In this video, we're going to talk about titrations and the titration experiment. Titrations are a way of figuring out what the unknown concentration of a solution is based on its reaction with a known solution. Most of the time, this will be in the context of an acid-base neutralization reaction. But sometimes you can actually do this with other kinds of solutions as long as the moles of one reactant equal the moles of another. So the molarity of one solution can be equated to the molarity of another one. So the titration formula is going to look very, very familiar to you. It's M times V equals M times V. And this is not a coincidence that this looks just like the dilution formula. It in fact is the dilution formula, and for exactly the same reason. Molarity times volume, recall, molarity times volume equals moles of solute. So in this case, we have molarity times volume of the acid. A stands for acid, and B stands for base. The molarity of the acid, the molarity of the acid times the volume of the acid equals the moles of acid. And what do we mean by moles of acid? Well, specifically, we always mean moles of hydrogen ion equal the moles of hydroxide ion. When we talk about acids and bases, remember, hydrogen ions and hydroxide ions. Those are the only two ions we care about in acids and bases. So that's what we're saying. And it's only at one point during a titration experiment where this actually holds true. So molarity times volume equals moles. Just like in a dilution, in the dilution process, when you dilute something, the number of moles of solute stays the same before and after. So the moles of hydrogen ion will equal the moles of hydroxide ion under specific circumstances or under specific conditions. Only at that point are we allowed to apply this titration formula. And that's okay because it is at that point that we can calculate the unknown variable. So a titration experiment is performed in order to determine the concentration of an unknown acid or an unknown base. It can work either way. And to tell you the truth, it can work for almost any two solutions. As long as you know the product, it can measure, and you can measure the exact point at which the molarities of the two reactants are equal, or the moles of each reactant is equal. Either you know the identity of the acid or the base, but not its concentration, or you may not know the concentration or the identity of the acid or base. Either way. In fact, we're going to do an example where we actually figure out the identity of the acid or base compound based on a titration experiment and working our way back through molar mass and then using the molar mass to figure out the identity. Titration experiments rely on neutralization reactions. Recall that a neutralization reaction is just a regular old double displacement reaction, only in this case it happens to be between an acid and a base. But just like a double displacement reaction, we're going to see ions change partners. We're going to see two different compounds switch their positive ions between them. Once the acid or base being analyzed, called the analyte. So by the way, the unknown, just some terminology here, the unknown compound or the unknown solution that you are analyzing is called the analyte. The solution that you are using to analyze the analyte or to figure out the analyte is called the titrant or titrant. Once the acid or base being analyzed is neutralized, the titration is immediately stopped. And the volume of the neutralizing solution called the titrant that was used is calculated or measured, however you want to say it. It's a simple calculation. It usually involves nothing more than a subtraction. It's important to stop the titration experiment as soon as you reach the point where molarity times volume or moles of acid equal the moles of base. If you go even one drop beyond that point, if you let even one more drop of titrant solution react with the analyte solution, this criterion ceases to be valid, and then the formula ceases to be accurate, and then your results are inaccurate. So if you overshoot the what's called the equivalence point, And we'll talk about that terminology soon. If you overshoot this equivalence point by adding even a little bit more of the titrant solution, a little bit more of the solution that you need to analyze the analyte with, you will actually overstate the amount of solution you needed to neutralize, and you will thus overstate the concentration of the solution that you are analyzing. You will overestimate or overcalculate that. Titrations use more precise glassware called burettes. Most of the time when you see a titration in lab, you're going to use a burette. And yes, that is the correct spelling, or at least that's one correct alternative. The other way is with 2 T's and an E. A burette is a long, narrow tube. It's good to down to 1/100th of a milliliter, so 2 decimal places when you're measuring in milliliters. So it's better than a graduated cylinder because they're more accurate or more precise to a greater degree. Also, another thing is that a burette has a feature allowing the experimenter to control the flow of titrant, stopping or slowing. It's going to be important to stop the experiment as soon as you reach the what's called the equivalence point, which I will define shortly. Maybe I should have said that first. As soon as you reach the equivalence point, of course, you're not supposed to just let the solution flow freely up until that point. You're supposed to slow down. You'll generally know approximately what volume you should reach to get to the equivalence point. If not the very first titration, usually these are done in triplicate, meaning you do the first one as a sort of practice one and to figure out approximately where your equivalence point is, the point at which your moles of acid equal moles of base. That's the equivalence point, where this formula holds true, where moles of acid equal moles of base. Moles of hydrogen ion equal moles of hydroxide. That is called the equivalence point. So you do the first titration to figure that where that is approximately. The second titration then, since you know when you're getting close, you can slow down the drip, the dispensation of your solution, of your titrant solution into the analyte. You can slow it down as you get closer to your equivalence point so that you don't risk overshooting it. You can, a burette actually allows you to to slow down the flow of solution down to maybe 1 drop a second, 1 drop every 20 seconds. So you can significantly slow down and control the mixing, how much of the solution you mix at any one time, so that you never have to add more than a drop extra, so that your error is controlled when you're adding solution together, when you're dispensing solution. So this will make more sense when you actually see the pictures. Before we continue on, let's go a little further. So a burette. This is a burette here. It's a long, narrow tube. Most burettes in undergraduate labs are about 50 milliliters. So you start, unlike a normal piece of glassware in the lab, you actually start at the top at 0 degrees Celsius. You fill the burette all the way to the top, and at the top, when the burette is completely filled to the top line, that is the 0 milliliter mark. And then as you lose, as you dispense solution from the bottom of the burette down at the tip here, as the solution's volume decreases, the actual numerical value increases in the burette. So you read this scale upside down. You start at 0, and as you lose more volume, you're actually going up in volume until you lose the maximum amount of volume, which is 50 milliliters for most burettes. So it's a reverse, or it's an upside down scale. And the reason for that is simple. When you're using a burette, you're not measuring how much you're containing or how much you're holding. You're measuring how much you're using. So the more solution or liquid that flows out of the burette, the greater the volume you have used. That's why the scale is upside down. The rotating handle here, here it's a red handle here. On this one in this picture, it's a blue handle. This little rotating handle is called the stopcock, and this is actually what you need to control the flow of your solution. When the stopcock is completely vertical, it stops the solution from flowing. Oh, I'm sorry, it allows the solution, excuse me, it allows the solution to flow through. So solution will flow through. But if you turn the stopcock horizontally 90 degrees, it stops the solution completely. But you can stop anywhere in between, at any point in between, any angle between 0 and 90 degrees, and you can allow for the slow drip of solution into your flask. Typically, you keep your analyte in a flask, and in what's called the Erlenmeyer flask, and you allow the titrant solution, the solution whose volume, whose concentration you allow the titrant solution to drip through or dispense through a burette into the flask containing the analyte. The flask will also contain an indicator, an acid-base, in the case of an acid-base titration, this is an acid-base indicator. By the way, if you want to see a video, a very short video, only about 3 minutes long, I think this is well worth your time. Just click on this video here. You can watch it on YouTube, or you can watch it directly in this window, but it's a little small. And it shows you a complete titration experiment. They do not take long. A titration experiment is a relatively short experiment once you have all your solutions ready to go. I mean, once you've set up your burette, cleaned it, and gone through all that procedure and made your solutions, the titration itself doesn't take more than a few minutes. And you get to the point, you start at a point where you have maybe, depending on what you're titrating, what your analyte is, you'll start usually with a clear colorless solution, and you'll add solution until the indicator, the acid-base indicator, changes color. So let's talk about acid-base indicators. So an acid-base indicator is any compound that you add to your solution. It doesn't react chemically with any of your reactants, but it does change color. All by itself, it changes color because depending on the pH environment of the indicator compound, it can change color. This doesn't interfere with the neutralization reaction, believe it or not. So in one environment, in one pH, the indicator compound will be one color, or it might have no color, it might be clear and colorless, and then at a different pH, it'll have a definite color. So there are indicators for almost any pH from 0 to 14. Some acid-base indicators only cover a narrow range, like say, for example, between pH 2 and 3, or some between 8 and 9, or whatever. Some, like litmus is a combination of many different compounds. It actually covers the full gamut from 0 to 14 pH. And you can see litmus comes as two different types. It comes in the form of paper, litmus paper, which are just little narrow strips of paper, upon which you'll put usually one drop of your solution to test its pH. And you'll notice the pH ranges from 0 to about 13 here. Actually, beyond 13, it will give you the same reading. But you can see the different hues of color all the way along. So depending on that, you basically dip or use a glass stirring rod to put a drop of the solution that you want to figure was pH you want to know onto your pH paper, and you look at the color, and sometimes you'll even just put the strip of paper right up against the scale that comes with the pH paper, and you'll just match the color to whatever you see. If it's yellowish, then it's probably around a pH 4. If it's bluish, it's usually a high pH around 11 or 12 or 13. Make sure you remember, litmus is always red, no matter what the brand of litmus, it's always reddish to pinkish at the most acidic ranges, and it's always bluish to maybe bluish purple at the most basic ranges. And in between, it ranges from orange to yellow to green. Even if you don't remember the middle ranges, just remember the extremes. Red for acidic and blue for basic, B for basic, blue for basic for litmus paper or litmus solution. Litmus can also be in the form of a solution. Notice the acidic solution is red and the alkali or base solution is bluish, purple, depending on how you see that. Now, the other that's a very, very common type of indicator. The other very common type of indicator used especially in school labs is phenolphthalein. Phenolphthalein has only two colors and it only changes pH. It has what's called an endpoint only right at neutrality, meaning once you go from a slightly acidic solution to either a neutral or basic solution, it undergoes an almost instant color change from clear and colorless remember, to describe a solution, you should describe its clarity and its color. Clear and colorless, immediately at anything above at pH 7 or above, pH greater than or equal to 7 goes to pink. And it goes up to maybe pinkish purple color, depending on the concentration and how much more basic you've made it. But it has only one point at which it changes color. This is referred to as the endpoint. The endpoint is not the equivalence point. The equivalence point is when moles of acid equal moles of base. Moles of hydrogen ion equals moles of hydroxide ion. The endpoint is the point at which the indicator, the acid-base indicator, or any indicator that you are using changes color at a relative place for you. So the endpoint is when the indicator compound or the indicator solution changes color. Once you've crossed that pH threshold, that's called the endpoint. The endpoint does not necessarily coincide with the equivalence point. Now for phenolphthalein, it does. But for litmus paper or litmus solution, clearly it doesn't, because it can go through all of these different pH changes. Not one of them, except for maybe the one at pH 7 would be the equivalence point. Okay. So just a little what's going on? Just a little review of neutralization reactions. I'm not trying to open any apps. Okay. Neutralization reactions review. Titration experiments rely on neutralization reactions. So what's a neutralization reaction? Just a little review here. This is going to look very familiar to you. For example, take sodium hydroxide and hydrochloric acid. Remember, hydrochloric acid, being an acid, behaves in water when it's an aqueous solution. It behaves just like any other ionic compound, even though it's not technically an ionic compound. It doesn't matter. All acids behave as if they are ionic compounds. So you're going to have the positive hydrogen ion leave behind the chloride and join the negative hydroxide ion. At the same time, the sodium is going to leave the hydroxide ion, which it already has, because once these compounds dissolve in water, they've already dissociated. And so what you end up with is sodium chloride, aqueous, dissolved in the water, and liquid water. So a product of any neutralization reaction is going to be water plus some kind of salt. And when I say salt, I don't necessarily mean, although in this case it's literally table salt, it doesn't necessarily mean table salt. Salt in chemistry simply means the ionic product of a neutralization, an acid-base neutralization reaction. Let's take another example. We have sodium bicarbonate plus acetic acid. Bicarbonate is actually the conjugate base of carbonic acid. But in this case, because it's a base and there is no carbonic acid around, in this instance, it will perform the function of a base. So bicarbonate is our base and acetic acid is our acid. So the hydrogen can join the bicarbonate to make carbonic acid or hydrogen bicarbonate and sodium acetate. Sodium acetate in this instance is our salt. Now, in this case, because the base we were using was not a hydroxide, a metal hydroxide base, it wasn't a strong base, this ended up not being water and salt, but an acid and salt. Remember, water is technically the acid or the conjugate acid of hydroxide. In this case, we ended up with the conjugate acid of bicarbonate ion, which is the acid, carbonic acid. Another example is soap made from lye. Lye is just sodium hydroxide, lye. Sodium hydroxide and a fatty acid. A fatty acid is an organic acid, like those carboxylic acids we talked about. So by now you probably recognize the COOH as representing the C double bond O, OH. That's our acid ending. And then here we have an 18 carbon chain When these react, the hydrogen here is going to join the hydroxide to make water, and then the rest of this will be sodium. This, for example, might be sodium, whatever this fatty acid is. I think it's sodium lauryl stearate or sodium laurate, depending on what fatty acid name this is. And you'll usually see these kinds of fatty acids, or at least by name, on shampoos, detergents, and soaps. So if you ever see sodium lauryl stearate, that is the soap. That's the part where the lye was added to some sort of fatty acid to make sodium lauryl stearate, which is just a long chain fatty acid compound, or acid, carboxylic acid, with a lot of carbons attached to it. So acid-base neutralization reactions are just double displacement reactions. Give me 1 second here. I don't know, for some reason it seems to think I'm trying to watch the video right now, but I'm not. Okay, so moles equals moles. That's the point at which a titration, everything about a titration hinges on the point at which the moles equal the moles. This is called the equivalence point. This is the #1 most important point in a titration. So the equivalence point, as I mentioned already, is when moles of acid equals moles of base. And we know that when moles equals moles, we know that molarity times volume equals moles. So molarity times volume equals molarity times volume. In a titration experiment, your goal then is to figure out the molarity of your unknown solution, usually. Now we're going to look at many different examples here. But your goal is to find the molarity of your unknown by finding out the volume of your unknown, which you determine, luckily, that's up to you, your volume of your known solution and your molarity of your known solution, which by definition are known. So you have 3 out of 4 of the variables in this titration formula once you finish the experiment. So once you finish the experiment, you have 3 out of 4 of the variables, just solve for the one you don't know. And that's what a titration is based on. It's the experiment. The point of the titration experiment is actually to tell you this piece of information here. How many milliliters, or what volume of your known concentration solution was required to completely neutralize your unknown solution? Once you have VA or VB, whichever one it is, I'm arbitrarily picking VA here to be the known. Once you know the volume of your known solution that needed to be used to neutralize your unknown, you have the very last experimental piece to plug in this variable V and then solve for M of the unknown. So it is at the equivalence point, and only at the equivalence point, that we can use the titration formula. For this reason, it is critical to stop the flow of solution as soon as the solution in the flask changes color. In other words, assuming that your endpoint does coincide with your equivalence point, that is. Most of the time, especially in intro chem, you will, and even the next semester chem, you will actually be using phenolphthalein, which does coincide more or less with the equivalence point. It's at the point of neutrality that the endpoint for phenolphthalein lies. So otherwise you will overshoot, now I'm saying this again, you will overshoot the equivalence point. If you keep adding more titrant solution after you've already reached the equivalence point, after your indicator already tells you, hey, you've done it, you've neutralized your solution. If you keep adding more after that, even a drop or 2 more, you're overstating your unknown solution's concentration by however much, whatever factor it is that you overshoot. By whatever factor it is, you're adding more and extra solution, because the entire experiment depends on you accurately measuring the volume of your known solution that was needed to neutralize your unknown solution. So if you overstate the value of your known, you've overstated the value of your unknown as well. The endpoint, as I mentioned, is the point at which your indicator changes color. Some indicators change color at different points than the equivalence point, so be aware of that. If you really have to know what you're doing. Generally speaking, phenolphthalein is changes color at neutrality. So it does coincide with the equivalence point, but others don't. Litmus, of course, has a whole bunch of different color ranges. And we'll see another one. Well, no, we'll see a non-acid base indicator in our last example. So that's not really going to be relevant there. So the endpoint sometimes coincides with the equivalence point, but not always. Just know your indicators, your acid-base indicators properties. Okay, let's do an example. The first two examples are going to be relatively straightforward. It's going to be monoprotic acid and monohydroxide base, and we'll just react them together and see what happens. So in our first example, we're going to read through the problem and we're going to collect the information as we read through the problem. So in a titration experiment, an unknown monoprotic acid. So we don't know the identity of the acid, but we do know the one most important thing. It is monoprotic. That means we have only one hydrogen ion attached, or one hydrogen attached to this acid. It's not going to donate more than that. So for that reason, the molarity of the compound equals the molarity of hydrogen ion. That is what that information is telling us. This is not necessarily true, and you cannot take this for granted. If I didn't tell you, you wouldn't actually know, and it would be an unknown, ambiguous problem. So what this says, by me saying monoprotic, it implies that the hydrogen ion molarity equals the overall unknown acid molecules molarity. They are not necessarily the same, not in a diprotic or triprotic acid. They would not be the same. But in this case, they are, because it's monoprotic. It's a 1-to-1 ratio of protons to acid molecules. Okay, so this monoprotic unknown acid is titrated with a 0.315 molar potassium hydroxide solution. This is our base. It is given, and so this is the molarity of our base. Molarity, base, 0.315 molar. I'm going to write that in. Potassium hydroxide, of course, is our base compound. Hydroxide is a base. It's a strong base. 32 milliliters of the acid are poured into an Erlenmeyer flask. Now note this, you get to choose your unknown volume. Your unknown, you don't know the unknown's concentration, but you do know its volume because it's your choice. You get to decide how much of the unknown solution you want to titrate. So you or somebody decided, hey, it's going to be 32 milliliters of the acid. So volume of acid is 32. Actually, I guess I went through the trouble of color coding, right? Why don't I use the color coding? 32 milliliters. So that is our volume of acid. It was particularly chosen. It could have been anything. There's nothing that says it has to be that value. You get to choose whatever it is you want. The burette, now remember that long glass tube, or usually plastic tube, is filled to the 22 milliliter line. Okay, so it's filled to the 22 milliliter line. Does that mean our volume of base is 22 milliliters? No. So 22 milliliters. This is not our volume. This is simply one component for us to figure out what our volume is. The burette doesn't tell you, can't possibly know what the volume of your acid is going, what the volume of your known is going to be at the beginning. At the end, when the phenolphthalein just changes color from clear to pink, that's the equivalence point, the experiment is immediately stopped before another drop is dispensed. Otherwise, you've overshot the mark. The burette now reads 46 milliliters. So we have 46 milliliters. This is our ending, this is the end, and we have our starting point on the burette. So we started with 22 milliliters in our burette. We ended with 46 milliliters in our burette. That gives us what? Subtract. So take the difference. That means we used 24 milliliters of base solution, potassium hydroxide solution, used. It's not the 46, it's not the 22, it's the difference between them. It's the amount that we used. If we started at 46, if we started at 22 milliliters and then we ended at 46 milliliters, then we used the difference between 46 and 22. That's our change in volume in the burette. That's how much we used. Remember, the higher up the burette you go, at the very beginning, you have the low numbers. And then as you use volume, the volume numbers get bigger, but that's because that's the amount you're using is getting bigger as you empty out the burette. Okay, so 24 milliliters is our VB. So the only thing we don't have now is molarity of acid. So that's the one piece of information we want to calculate. We arrived at this experimentally. This was the point of the experiment, to figure out what the volume of our known solution would be in order to completely and exactly neutralize the unknown solution. The rest of the information here was already known or given. Known or chosen by us. Known before experiment began. This was known, the molarity of the base was probably chosen either by you, or you made a solution and standardized it just for the purpose of this, or it was given to you by the stockroom or your lab stockroom or whatever, and it was not chosen by you, but it was known beforehand. So neither of these two variables were experimentally determined. They were simply given. The only part that was determined in the experiment is the volume of your known solution. And so you plug everything in. And so we use our formula now. Molarity of acid multiplied by the volume of acid equals the molarity of the base multiplied by the volume of the base. Plug in your number. Well, actually, let's solve first. Molarity of acid is going to equal molarity of base times volume of base divided by the volume of the acid. So now we just plug in our numbers. So we have, I'll stick to the color coding. So the molarity of base was 0.315. I'm having a hard time seeing. Sorry about that. There's a lot of glare in this room. 0.315 molar. That's our molarity of base. Volume of the base was 24 milliliters. And we divide that by the volume of the acid, which was 32 milliliters. Note, by the way, again, that our milliliter units are going to cancel out. So it's really not necessary in this particular instance. And generally speaking with titrations, it's usually not all that necessary to convert to liters because your volume typically cancels out. Just like with dilution problems, your volume cancels out, so it doesn't matter if you convert to liters or not. We're not calculating moles right now. We are going to look at some examples where we do go directly to moles instead of passing, trying to figure out molarity. In that case, you will have to get those units straight. You'll have to use liters or whatever the appropriate unit is. Okay, so what does that get us? Well, we take our 0.315, multiply by 24, and then we divide that by 32. Now, before we even hit the calculator buttons, let's think about what we're looking at here. Let's just think. Think for 1 second. Don't calculate just yet. It took us 24 milliliters of this base solution to neutralize 32 milliliters, or put it the opposite way. It took 32 milliliters of this acid solution to neutralize the 24 milliliters of base solution. Either way, they were both completely neutralized once they entered the flask. What does that mean? Well, if it took a greater volume of acid than base, or if it took a lesser volume of base than the acid, that must indicate that the base has a stronger concentration or a higher concentration. So my guess is that our acid, our molarity of acid, is probably going to be less than the molarity of base by about I'm going to say, let's see, it's 8 milliliters less, or in other words, it's about 33% by approximately 33%. So I'm going to guess that the molarity of the acid is about 33% less than, not 33% of, but 33% less than the base. And I'm basing this only on the fact that it took 8 fewer milliliters to neutralize the acid of the base solution. It took 8 fewer milliliters, 24 versus 32, and 8 out of 24 is 33%. That's what I'm guessing. And 33% of 0.3 is about 0.1, so 33% less. I'm guessing it's going to be about 0.2 something. That's just my guess. I don't actually remember the answer to this problem. So let's see. Either that or I've made a fool of myself, one or the other. Times 24 divided by 32, I get 0.236. 0.2, so approximately 1/3, maybe a little bit over 1/3, but approximately 1/3 less. 0.1 less than 0.3 is 0.2, 0.23. That was just my guesstimate. I wasn't actually doing any real calculating per the formula. I was just noting that it took a lot less base to neutralize more acid. Therefore, the acid must be less concentrated. So that is our answer, molarity of acid. 0.236 molar, our unknown acid. I'm just going to designate, since I don't know the identity of the acid, I'm just going to write HX. HX is a stand-in for an unknown acid. Since I don't know what, I know it's an acid, so it has H. I don't know what the X part of this unknown acid is, so I'll just write X. X means I don't know. I could write H question mark. If you really wanted to do that, you could do it that way too. So there it is. So this makes sense. It makes sense that our concentration, our molarity of the acid is less than the base because it took less base solution to neutralize more acid solution. So there's a logic behind this. It's not just number crunching. You can actually see it working out. So always do this. Whenever you have the opportunity, take the opportunity to estimate what your numbers should be based on the data that you have in front of you. Don't just let the calculator do all the calculating for you, because if you do that and you punch in the wrong number, you won't be able to tell that you did it wrong. If you made a mistake, just an accidental mistyping of a button, you won't know it unless you already have a clear idea of approximately where you need to be. So always think about your numbers. This part here is simply the same thing written out, 0.236, do we agree? Oh yeah, there it is, 0.236. So same thing, I just wrote it out here. It's worked out for you in case you want to look at the PowerPoint again without rewatching the video. It's here for you in this particular example. I don't do that with all the examples, but this one I'm leaving for you. That's because this is such a standard basic titration problem. So, you know, you're going to, all of them basically look like this, all the typical titration problems. Let's do another example though. So in a titration experiment, hydrobromic acid, so this is so as you know, hydrobromic acid is a binary monoprotic strong acid, HBr. It's a monoprotic strong acid. That's all you really need to know. Of unknown concentration is titrated with 0.630 molar lithium hydroxide solution. Okay, so let's start making a little table for ourselves. We have molarity of acid. Well, we don't know, so I'm going to put a question mark. We have volume of acid. I haven't read it yet. We have 0.630 molar lithium hydroxide. That is our molarity of our base solution. So I'm going to fill in my table for that, 630 molar. And then I have volume of base. Let's see, 28 milliliters of the acid are poured into a flask. Okay, so that is our volume of acid, 28 milliliters. Are poured into an Erlenmeyer flask. Usually the Erlenmeyer flask is the one that holds your analyte plus your indicator. The burette is filled to the 17.81 milliliter line. So the volume of the base, that is not the volume of the base. Now be careful. The volume of the base is going to be something minus 17.81 milliliters. So 17.81, we start, that's our starting point. start at 17.81 milliliters. And then during the experiment, I'm going to use up a certain volume of this base solution. And then at the end, when the solution in the flask turns pink, when I've reached my endpoint / equivalence point in this case, the burette reading is 37.25. That's, oh, sorry about that. That is our final volume, but again, that is not our volume used either. Neither one of these numbers independently are our volume. Our VB is going to be the difference between these numbers. Our delta V equals our VB. And so that's 37.25 minus 17.81. And if I type that in, I get 19.44 milliliters of VB. That is our experimentally determined volume. That is the main thing that the experiment, the titration experiment, gives us, the volume of the known solution required to neutralize the unknown solution. After that, that's our final, or not our final piece, but that is the final known variable with which we can finally solve for M, in this case, MA, the molarity of the acid. So molarity of the acid is going to equal the molarity of the base, 0.630 molar, multiplied by the volume of the base, 19.44 milliliters, divided by the volume of the acid, 28 milliliters. And again, think it through. Before you even bother calculating, just realize 19 divided by 28 is a fraction less than 1. So we're going to see a molarity that is less than 0.630. And again, it has to do with the fact that it took 28 liters, or we neutralized 28 milliliters of acid with only 19 milliliters of base. Therefore, the base must be more concentrated to be able to do that. The base is punching above its weight class, in a sense, if you understand that terminology. So we get 0.437, 0.437 molar hydrobromic acid. This time we know the identity of the acid, so I'm just going to write it in, and that is our answer. So make yourself a little, just like you would with a gas law, like Boyle's law, P1V1 equals P2V2, or like with the dilution problem, M1V1 equals M2V2. Set up a little table for yourself and just read through the problem. And sometimes, don't worry, if it takes you more than once to read through the problem, that is okay. Read through it more than once. Read through it as many times as you need to put down all of the pieces of information, to fill in all the information you need, fill in all your knowns, and then solve for your unknown. Okay. And again, this is the worked out solution. You can see it right here. Yet another experiment. Now, this one is not exactly the same as the others. This time, we're dealing with something that has two hydroxide. We're dealing with a base that has two hydroxide ions in it. So we have to be a little careful here. There's going to be an extra step. This isn't just more of the same. So in a titration experiment, a calcium hydroxide solution of unknown concentration is titrated with a 0.4 molar hydroiodic solution. Okay, so let's start writing in all of our stuff. Molarity of the acid. So hydroiodic acid is our molarity, 0.400 molar HI, right? That's our acid solution. Our molarity is given to us for the acid solution. Okay, let's see, volume of acid, let's see, 50 milliliters of the base. Okay, I don't know yet, so I have to keep reading, but let's see, molarity, MaVa MB, and then VB. Well, clearly we're not gonna know, since it says unknown concentration of this base, we're just gonna put a question mark there. We can't possibly know that yet. VB, okay, how about VB? 50 milliliters of the base analyte are poured into an Erlenmeyer flask. Okay, so 50 milliliters, that's a lot. That's kind of risky because most burettes only hold about 50 milliliters of solution. So you might risk running out of solution in your burette, at which point you have to restart the experiment. Okay. The burette is filled to the 38.75 milliliter line at the beginning. Okay, this is the acid now. Even though it doesn't say so, remember the 50 milliliters we picked went into the Erlenmeyer flask. The unknown always goes into the flask. So the burette is filled with your titrant solution, meaning the solution that you are going to use to analyze the analyte solution, the unknown solution. Okay, so the burette is filled to the 38.75 milliliter line at the beginning. Wow, that's cutting it close. 38.75 milliliter, that's practically near the bottom. I mean, at the end, when the solution in the flask turns clear, now this time the solution turns clear, that means it started pink. Why is that? It started pink because the indicator was sitting in a base solution. Because it was sitting in a base solution, it started off pink. And then as you add acid and neutralize all that hydroxide and the pH comes down to neutrality and less than neutrality, it goes from pink, which is the basic indication, to a slightly, ever so slightly below neutral, which is clear to indicate that it is no longer basic. All the hydroxide is gone. So 38.75, 49.65 is the final volume. So we take the difference between them, and that gets us, I believe it's 10.90 milliliters. But I'm not going to leave it up to my faulty mental calculator here. I'm actually going to do it. I've learned my lesson. Not that you can't make mistakes on a calculator, you sure can. Anyone can. 10.9, okay, 10.90 milliliters. Notice I have 2 decimals because even though that was a 0, I have to write it because the burette readings are good to the hundredths place. Okay, so my volume of acid, which is my known, is 10.9 milliliters. I used 10.9 milliliters. So 0.4 times 10.9 molarity, okay. Now there is going to be a little wrinkle in our setup. Our final answer is not simply going to be the molarity of the base. Why is that? Because the molarity of the base isn't really the molarity of the base solution. In fact, let's make this more obvious. What I'm really solving for here is the molarity of hydroxide ions. That's what I'm actually solving for. In fact, it might even be more honest to say bracket hydroxide ion, because that's what I'm actually solving for. I'm not solving for the actual calcium hydroxide. I'm solving for just hydroxide. If I want to know the molarity of calcium hydroxide as a whole, as a compound, I'm going to have to make an adjustment. Well, let's first figure this out. So our molarity of base, or i.e. hydroxide ion, is going to equal MaVa divided by Vb. This part is all the same, right? MaVa over Vb. So we plug in our numbers. Molarity of acid is 0.4 molar, hydroiodic acid. Volume of acid is 10.9. This isn't a fraction, by the way. This is a subtraction up here leading to the result, 10.9 milliliters. And I divide by the volume of my base, which was 50 milliliters. And so what does that get me? Well, it's going to give me approximately 1/5 of 0.4, a little bit more than 1/5 of 0.4. So probably about, I don't know, 0.085 or something, or 0.083. .087. Oh, wow. Okay. So that's 0.0872 is what I got. Molar hydroxide ion. Now be careful. This is not actually calcium hydroxide. This is simply hydroxide ion. If it's a 1-to-1 ratio between hydroxide ions and the compound, in other words, if the compound itself has only one hydroxide ion, like for example, sodium hydroxide, rubidium hydroxide, lithium hydroxide, then there's no issue. But this is calcium hydroxide, which has 2 hydroxides for every 1 calcium hydroxide. So we better adjust. Rarely ever do you want to know just the molarity of a particular ion. Usually when you try to figure out the molarity, you want it for the entire compound. If you're labeling the reagent bottle, you never just label it by one particular ion, because you have no idea what the person needs it for. They just need to know how much total compound, how many moles of formula units or how many moles of molecules are in the solution. So what I'm going to do here is I'm going to take my molarity of hydroxide and I'm going to convert it. And I'm going to do this systematically, even though there's plenty of logic in here to indicate what it actually is. I'm just going to do this systematically. I know that for every 1 mole or every 1 molar of hydroxide, oh, I'm sorry, not 1 molar. Sorry, I had this back here. I know that for every 2 moles per liter, or 2 molar of hydroxide ions, according to the chemical formula, okay, that didn't work. Let's try that again. 2 and 2. It's a 2-to-1 ratio of hydroxides to calcium hydroxides. So every 2 molar hydroxide is 1 molar calcium hydroxide. In other words, we have half as much calcium hydroxide formula units as we have hydroxide formula units, because there are twice as many hydroxides for every calcium hydroxide, right? It's a 2-to-1 ratio. Every one of these gets us 2 of those, 2 pieces in every one. So it's half. So instead of being 0.0872, it's 0.0436 molar calcium hydroxide. So just be careful. Even though it says MB, molarity of base, or VA, MA, molarity of acid, what you're actually solving for, and I've said this from the very beginning, if you notice, I specified back here, where is it? Moles of hydrogen ion, moles of hydroxide ion. It's never been about the entire compound when you're solving here. It's always about the individual ions reacting together to make water. That's the true neutralization. It's when hydrogen ion and hydroxide ion combine to eliminate each other and to form water instead. Where am I? Okay, so, oh wow, I didn't notice. See how close these are? That's pure coincidence. I had no idea these numbers were going to be almost identical. 0.437, 0.436. Anyway, oh, 0.0436. Never mind. Okay, it's a lot smaller. So 0.0436 is our final answer, as long as I can double check this. 0.0436, yeah. Molar calcium hydroxide. This is our answer. This was not our answer. This was the amount of hydroxide. What we wanted to know, though, was the amount of calcium hydroxide, the entire formula unit. There are fewer of the formula units than there are of hydroxide ions, because every time calcium hydroxide goes into the water, it splits up into 3 ions, 2 of which are hydroxide ions. And remember, a titration is only measuring the hydroxide ions against the hydrogen ions. We don't care about the calcium ions. So this is a 2-to-1 mole or molar ratio of hydroxide ions to calcium ions, just like the chemical formula. The empirical formula tells us. That 2 in the empirical formula is what's informing us. If you understand that, then there's going to be a lot of things that are not going to be a problem for you. Okay, now here's another thing, an interesting thing you can do. You can actually figure out the molar mass of an unknown compound. But it depends on you knowing the mass of the compound that went into solution. So in this case, I know I've been calling it the titration formula, but in this case, you don't even need the second half of the titration formula. All you really need is molarity times volume equals moles. So in this case, you won't even need the other half. It's not MaVa equals MbVb, it's just MaVa equals moles of A, which equals moles of B. In fact, instead of saying that, let me write that down for you. This problem is going to be about figuring out an unknown molar mass, which means in this problem, we're going to calculate MaVa equals moles of A, which at the equivalence point equals moles of B. And this is the critical point here. We don't, remember, there's more than one way to get to moles of something. We've been using molarity and volume because that was the information we had to work with. But in this case, there's not going to be any volume of base. There isn't going to be a molarity of base. So we're going to have to take this step by step. So as always, when you don't know exactly what to do, this is my advice to you for all situations, not just in chemistry and not just in intro chemistry, but when you don't know what to do, write down what you know, organize it, stare at it, and think about the ways you can relate what you do know to what you don't know. That's what all of this has been about. Okay, let's take a look. So a solution of 0.317 molar hydrochloric acid. So what is that? That's our MA, molarity, right? MA, it's telling us that it's 0.317 molar of our acid. Is titrated with a solution made by dissolving 423 milligrams of an unknown base in deionized water. Okay, what that means is, what it's saying is, we have 423 milligrams. I'm just going to right away convert milligrams to grams. 10 to the third milligram, 10 to the third milligrams gives me 1 gram. That's going to equal 0.423 grams of my unknown base in deionized water, but it doesn't specify how much. So volume of base, unknown. In fact, not only unknown, but unknowable. Molarity of base, unknown, and frankly, at this point, unknowable. So the entire right side of my formula is missing and irretrievable. Okay, well, let's keep reading, and maybe we'll figure out what to do. It requires 8.9 milliliters of hydrochloric acid to reach the equivalence point. Okay, 8.9 milliliters of HCl. So that's our volume of acid equals 8.90 milliliters. To reach the equivalence point with 46.7 milliliters of the base. Oh, I take it back. I guess we do have some volume information. Volume of base equals 46.70 milliliters. Okay, well, we do have the volume of the base. What is the molar mass of the unknown compound? The molar mass. Okay, what does molar mass equal? Molar mass equals grams of compound divided by moles of compound. That's the definition of molar mass, right? It's just those two units in a fraction. If you can figure out your grams of the compound and you can figure out the moles of your compound and you divide the grams number over the moles number, you will get the molar mass. So the question is, well, I have grams, don't I? I already have grams. So the top of this fraction was given to me. So that's going to equal 0.423 grams of compound, of my unknown compound, divided by X number of moles of compound. Now, I don't know the number of moles. Maybe we can figure it out. How do we get moles of compound? Oh, look at that. Here's a nice formula. That's right. Moles of A equals moles of B. But can I rely on the fact that my moles, remember this calculates moles of hydroxide, not moles of compound. Can I rely on the fact that moles of hydroxide will be the same as my moles of compound? Yes, only because I have been told to do that. This here allows me to make that assumption. This allows me to make that leap, assuming it has one hydroxide ion. In other words, the moles of hydroxide ion equal the moles of base compound. The moles of compound and moles of hydroxide are the same. It's a 1-to-1 ratio because this compound has only one hydroxide. Great. So whatever this is, it's some sort of base. I won't put B because I don't want anyone to think it's boron. It's not. I don't know what it is. Well, actually, we can probably figure it out. But hold on. I'll put X here. XOH is the formula. Where X, it's not xenon, where X is unknown. We don't know what X is, but we can figure it out. So let's see. So all we need to do is figure out how many moles of hydroxide ion we have, and then we'll know how many moles of of X hydroxide do we have? Well, how do we do that? Well, we can figure out how many moles of acid we have. Well, how do we do that? Well, we take the molarity times the volume equals the moles. What do you know? I have molarity times volume. They're right here. So I take my 0.317 molar and I multiply it. Now this time I better convert because I'm trying to convert mole. I'm trying to figure out or calculate moles. So in this case, I better convert this to to liters, excuse me. So it's 0.0089 liters. Convert to liters to get moles. It's not optional. This time it's not optional because nothing on the right, there is no right side of this formula. Nothing on the right side is going to cancel out our milliliters if we don't do this. So we better be very careful. So 0.317 times 8.9. Having a hard time pushing my buttons. I get 2.821 times 10 to the minus 3. 2.821 times 10 to the negative 3. That is moles of acid or moles of H+. But we know that that equals moles of hydroxide. And we know that that equals moles of X hydroxide, our unknown compound, right? We know this is all a 1:1:1 ratio because we've been told to assume it, because this tells us that moles of hydrogen ion equal hydroxide ion at the equivalence point, and we know we reached the equivalence point. So all of this is legit. These are justified assumptions. At the very least, the only one that's slightly less justified is the one where the problem has told us to assume it. It's not backed by logic, but just your faith in the problem writer's abilities, which is mine. So I'll leave you to your own conclusions in that respect. Anyway, so what this ultimately means is that our moles of unknown compound are 2.821 times 10 to the minus 3. No calculation needed. We know they're all the same value. Moles of compound. So all I do is put that in here. Now I have my grams, I have my grams divided by my moles. That fulfills the definition of molar mass. So let's do that. Let's substitute for X. Let's put the 2.821 times 10 to the negative 3 moles of compound in there. And what do we get? And let's do the division. Let's see what we get. So 0.423 divided by 2.821 raised to the negative 3 power. Obviously, I'm using the scientific notation function on my calculator. I get 149.9 grams per mole. That's our final molar mass. That answers the question. What is the molar mass of the unknown compound, assuming it has one hydroxide ion? Okay, great. Do you think we can figure this out? We can, and I think you know that because I'm asking the question. 140, basically 150, but whatever. We can round to 150 because it'll be close enough to whatever answers. We can figure out the identity of this compound based on its molar mass. It's actually fairly easy to figure out because we've only got about 6 choices. You might ask, well, what 6 choices do we have? In fact, I'm not even sure it's 6. Actually, if you really narrow it down, we only have about 3 reasonable choices of what this compound could be. And we can certainly figure out of 3 different possibilities which one this is. By the way, do we have any more room? No, we don't. Okay. I'm going to have to do a little bit of erasing now. So, take a screenshot or write your notes or just mark the time if you want to come back to this later, because I got to erase some of this now. All right. What are our 3 choices here? Well, let's think about this. This is a monohydroxide. This is, or I know I told you not to use mono. This is a compound, a base compound with only one hydroxide in it. What does that mean? That means we're limited to X being only a few possibilities. It must be a group 1 hydroxide because those are the only ones that have 1 hydroxide. On top of that, group 1 is obviously going to exclude H because if it's HOH, that's water, so that's out. So we can eliminate the first element in group 1. Well, what else is in group 1? We have lithium ion. So H is out, so eliminate that. We have sodium. We have potassium. Here's the thing though, we only have 1 hydroxide and 1 metal, right? That has to be the formula. You can't have more than 1 metal because hydroxide has only one negative charge. Therefore, our metal must have only 1 positive charge. If we have more than 1 metal, that would give each metal a charge of half or some fraction. That doesn't make any sense. So hydrogen is out. We have lithium, sodium, potassium, rubidium, cesium. Let's go through this. Let's add them up. The total molar mass is 150. Let's just say 150. Let's just make the math easier on ourselves. 150. What that means is that X, our unknown metal, plus hydroxide, the molar masses are going to equal 150. Hydroxide is equal to what? 16 plus 1, which is 17. Therefore, X plus 17 grams per mole equals 150 grams per mole. All I'm doing is using the basis of figuring out the molar mass of a compound. Only in this case, I don't know what one of my elements is. So X is going to equal 133 grams per mole. Whatever my metal is, it's about 133 grams per mole. Oh, well, guess what? Lithium is only about 7 out. Sodium is only about, look at the periodic table, by the way. I don't make a big fuss about this, but I do memorize some of these numbers, but that's just from repeated use, not for any other reason. Sodium is about 23, right? That's out. Our X metal must be 133 grams per mole. That's really heavy. It must be pretty far down the periodic table. Let's just keep going. 7, 23, 39.1. Again, if you just double check my numbers on the periodic table, you'll see all of these are out. Rubidium. Okay, finally we reached a number that I don't know. Rubidium, 85.5, 85.5. Nope, still too small. Cesium, what do you know? 132.9. Well, what do you know? 132.9, cesium is it. Okay, that was an attempt at drawing a star. 132.9 plus 16 for oxygen plus 1 for hydrogen gives me 149.9 grams per mole. My compound is cesium hydroxide. That is the identity of my compound. So not only were we able to figure out the molar mass, but we were actually able to figure out the identity of the unknown compound because its molar mass gave us a real clue. Plus, the fact that it only has 1 hydroxide narrows the field down. It eliminates all but the first column of the periodic table, and it eliminates hydrogen because hydrogen hydroxide is water. So we really only had 1, 2, 3, 4, 5 choices to choose from, but really only the heaviest ones were really reasonable given such a large molar mass. We knew it couldn't be some lightweight element like lithium or sodium bonded to the hydroxide. It had to be something relatively heavy. And so only the metals or only the elements near the bottom of the periodic table are going to be heavy enough to add up to 150 grams per mole with only a 17 gram per mole addition from hydroxide ion. Okay, so by using titration, you can actually not only identify the concentration of an unknown solution, but you can actually identify an unknown compound. Remember, where did all of this information come from? It came from figuring out the volume of your known that was required to neutralize your unknown, even if you don't know what the molarity or the volume of your unknown is. By the way, do you notice something? Nowhere in this problem did we ever make use of the 46.7. It was completely useless. That was just extraneous information. It made absolutely no difference whatsoever how much water you dissolve your compound in. If it had been 100 milliliters or 10 milliliters, well, other than the fact that you needed to dissolve the compound, you need enough water, it made absolutely no difference. As long as you have enough water to dissolve your compound, that's all you need. Its concentration did not matter. We never found out the molarity of the base, although we could figure it out now, right? If we wanted to, we could. We know the molar mass and we know the number of grams. You can just convert from grams to moles and then divide by the number by the volume, and then we could figure out the molar mass if we really wanted to. But what's the point? We already figured out what we wanted to know, the actual identity of the base of this monometallic hydroxide, or this monohydroxide metal compound. Okay, I hope that was interesting. Let's do another example. This one, again, is going to be a little bit different. There's going to be a little bit of a wrinkle. But if you can handle these little wrinkles, which is more my goal for you about being able to handle multiple ions and realizing the relationship between the number of ions in a compound and the number of compounds is not always one-to-one. If you get that point, you're golden as far as all this is concerned. Okay, so let's give this a try. So a solution of 0.1, by the way, the whole setup of this is very similar to what we just did. Again, it's going to be another MA times VA equals moles of base. That's what we're going to do. The only wrinkle here is that we are going to have a compound that has two hydroxides per formula unit. That's the difference. That's the only difference. So let's go quickly step through this. Molarity of acid equals point, you know what, I'm just going to start filling it in. I think you know the rest of this now. 0.189 molar. So that's our MA, multiplied by our volume, 23.6 molar. Of course, we need to convert that to liters, right? We need to convert from milliliters to liters. Otherwise, we're not going to get moles, we're going to get millimoles. And there's a time and place for millimoles, micromoles, nanomoles. Even in medicine, sometimes you'll get reports about blood work that is reported in micromoles or nanomoles. All right, so it's not unheard of. And in fact, in the very next example, we're going to apply metric prefixes to our moles or our molar units. So there's nothing wrong with that, but in this case, molars and moles, since we're using straight up molar, we better use liters as our volume unit to calculate moles. So our moles of hydroxide is going to equal whatever that is. 0.189 multiplied by 0.0236 liters. That gets us 4.46 times 10 to the negative 3. By the way, that's 4.46 millimoles if you really want to know. That would be 4.46 millimoles, but we're not going to report it that way. Moles of hydroxide ion. Remember, even though we talk about molarity of base, molarity of acid, we're not really talking about the compound, the base compound or the acid compound or acid molecule. We are talking about hydroxide ions and hydrogen ions. So we need to understand that so we can, when it comes down to it, when there is a difference in the number of moles and the ratio of moles of hydroxide to moles of compound, we are ready for it. So let's convert this. So I'm going to use, let's use light blue. So what I need to do is I need to recognize that there are 2 moles of hydroxide for every 1 mole of the formula unit. So that's going to be XOH2. Again, I'm using X because I don't know what the metal is. I'm assuming it's a metal. Actually, it has to be a metal. If it's not a metal, then this most likely is not a base. There is such a thing as borohydrate, but BOH actually does not produce a base. It actually acts like an acid. So it has to be a metal hydroxide, and there must be 2 of those metals. In fact, you know what? Here, tell you what, instead of using X, let's use M, because we know this is a metal. We know this is a metal hydroxide. That's not molarity. Oh, you're going to think it's molarity. Whatever. Okay, it's not molarity, right? That's 1 mole of metal hydroxide. M equals unknown metal. So keep that in mind when that's too many capital M's around me. Well, you know, I underline my capital M's for molar. All right. So that's going to equal what? Well, half, right? That's just half the value. 2.23 times 10 to the negative 3 moles of metal hydroxide, unknown metal hydroxide compound. So now we have our moles of metal hydroxide. Great. How do we figure out, let's see, what is the molar mass of the unknown compound? Well, let's figure it out. We have been given the grams. We would not be able to figure this out unless we were told the number, well, actually we've been given milligrams. So we have 271.2 milligrams of metal hydroxide, right? We don't know what the metal is. That's all we don't know. We know that it contains hydroxides. We know that it contains 2 hydroxides per formula unit. So let's figure that out. You might be wondering if it's possible that it's M3OH2. No, that would be impossible because that would give the metal a fractional charge. Okay, so we know that every 1,000 milligrams is 1 gram. So let's convert this over. So 271 divided by 1,000 is 0.2712 grams. So all I did was 1, 2, 3. That's all I did. 0.2712 grams of our metal hydroxide compound, our unknown metal hydroxide. So the molar mass or the molecular weight, let's say molar mass because it's not a molecule. Molar mass equals grams divided by moles, which is going to equal 0.2712 grams divided by 2.23 times 10 to the minus 3 moles. 2.23 times 10 to the minus 3 moles, grams per mole. All we're doing is filling the definition up for grams per mole or molar mass, I should say. So if I do that, 0.2712 divided by 0.00223 gives me 121.6 grams per mole. Okay, that is our molar mass, and that is the answer to this question. But again, maybe, I don't know, I'm not entirely sure, but I think I'm hoping, I'm hoping we can actually figure out what this compound is. We might not know, but let's give it a try. Let me just double check my math here and make sure I did everything I intended to do. 0.189, 0.0236 liters, 4.46 divided by 2. Every 2 moles gives me 1 mole of that. Okay. $271.2 milligrams. Okay, so let's see. How would we figure this out though? Well, again, if our total molar mass is 121.6, that means that the sum of all of our components should add up to 121.6 grams per mole. I'm just going to leave off the grams per mole part. So M is our unknown metal plus how many hydroxides? 2 hydroxide ions, right? Because we have 2 hydroxide ions in our formula. So it's going to be M plus 2 times 17 equals 121. Again, what does hydroxide equal? It's 16 plus 1 equals 17 grams per mole. And I keep telling myself I'm going to write a little bit more neatly, grams per mole. There we go. So that's where if you're wondering where I'm getting this 17 all the time, 17 is simply hydroxide ions molar mass. or yeah, molar mass. So M plus our unknown metals molar mass, or atomic weight, I should say, plus 34 equals 121.6. Therefore, M equals 121.6 minus 34. So that's going to equal 87.6 grams per mole. This is the atomic weight or atomic mass of our unknown, not our unknown compound, but our unknown metal. We already know what half of, or 2/3 of our compound weighs. We know the 2 hydroxides weigh 34 grams per mole. We need to know the metal so we can put all of this together. So what metal? Let's scan the periodic table, right? Scan the P table. Find a metal. Oh, and by the way, find a metal that can take on 2 hydroxides. Immediately you can eliminate group 1, because group 1 can only have 1 hydroxide because they are positive 1 metal ion. So eliminate column 1 from your search. So you can eliminate column 1, and you can eliminate column 3. You can eliminate aluminum. Aluminum out. Gallium out. Indium out. Why? Because they take 3 hydroxides. So that leaves what? Well, that leaves either your alkaline earth metals, column 2, or some kind of transition metal, right? Because the transition metals can also have positive 2 charges. You're looking for a metal with a positive 2 charge because you want a metal that can take on 2 hydroxides. That's either going to be column 2 or D block metal, one or the other. Let's scan column 2 first. So if I go through column 2, I see 87.6. So I go through column 2. Again, I'm going to have to do some erasing here. Let me just erase some of this. While I'm doing this, I'm hoping you're scanning through the periodic table, column 2 especially. But again, it could be a D block element, but it's 87. Yeah, I mean, that's pretty heavy. I don't know. It's heavier than most of the first row transition metals. So I'm guessing this is going to be on row 5 or 6. Yeah, our heaviest first row D block element, zinc, is already 65, I'm sorry, not already, is only 65.4 grams per mole. So it's definitely not the first row of the D block. Let's go to row 5. Row 5, we have what do you know? Strontium, the very first column 2 element on row 5. Strontium equals 80, what was it again? 87.62 grams per mole. 87, that is not a coincidence. Yeah, it's not going to be yttrium, that's even higher. So strontium hydroxide. So our compound then is strontium hydroxide. Look at that. Again, using the molar mass and scanning the periodic, just scanning the periodic table, just looking at the periodic table and looking for numbers that match. So our compound then is strontium hydroxide. That is our unknown, that's the identity of our unknown compound. We figured out the molar mass, but we took it one step further and we were actually able to deduce the identity from the molar mass by doing a little bit of subtracting, because we knew that the formula contained 2 hydroxides, each of which weighs 17 grams per mole. So we take away 2 17 pairs, or how do I say this, 2 sets of 17, that's 34. 121 minus 34 gave us 87. What metal that would be linked to 2 hydroxides weighed 87? It would have to be either column 2 or D block. What do you know? It turns out to be a column 2 alkaline earth metal. So there, we figured out the molar mass and the identity of an unknown compound, but this time with 2 hydroxide ions. But remember, We had to make this adjustment. We could not assume that the answer to our number of moles of hydroxide was the same as the number of moles of our compound. Always pay attention to the empirical formula. The chemical formula of the compound gives you the ratio, the mole to mole ratio, not only of between the elements, but from the element, any given element or set or combination of elements to the entire compound. It's always a ratio of some number to 1 of the entire compound. And you're not limited to one element. You can have groups of elements. You can have water. You can say how many moles of water in this hydrated compound. You can have how many moles of hydroxide ion in this one compound. How many moles of carbonate ion in this one carbonate compound. You can do that. You can answer any question you need to answer this way. That's my point, is that you have the information, and you have the tools. You just have to know how to use them. These are not basic questions, okay? I want you to know that. Other than the first two examples are basic titration questions, these are a little bit more advanced. I just want to let you know that these are not as straightforward as you're likely to find. These are the kinds of questions you will get in the next chemistry class, especially the very next one, the very next example we're going to look at. This is one of the labs from the next chemistry, from one of the higher level chemistry classes. Depending on, like time of year or who your lab instructor is, etc. I personally have done, I've done this one in the next level chemistry class, but not, I'm not guaranteeing it, but I've done this. I've done this experiment with my class. Okay, so titration beyond acids and bases. Titration isn't just useful for acids and bases. And one really important compound is used as a chelating agent. Ethylene diamine tetraacetate, EDTA. EDTA for short, and you're going to use that for short. We're not going to say ethylene diamine tetraacetate. By the way, when this is written out, it's written out without spaces, which is really ugly to read. EDTA was first used in the 1950s for the treatment of heavy metal poisoning. If you ingest lead or zinc or even mercury, as long as it's not organic mercury, which if you do, there's really no coming back from that, but just regular mercury, most likely you'll get some kind of chelating agent, and very likely that chelating agent will be sodium diacetate, sodium ethylene diamine tetraacetate, sodium EDTA, or sodium calcium EDTA. You'll get something like it as a chelating agent. What's a chelating agent? Chelation or chelating agents seek out, they're compounds, and this is, by the way, this is the formula, or actually I should say the structure of EDTA. They seek out metals and they trap the metals almost like they're trapping them inside of their claws. Think of these as 6 fingers. Is it 6? 1, 2, 3, 4, 5, 6, 7. Oh, sorry, 7. I even counted it earlier and 6. Sorry, this is not one of them. Yeah, it is 6. Okay, I knew it was 6. Think of it as trapping it between 6 fingers and holding the metal in place. Meaning if you have dissolved lead ions or calcium ions or magnesium ions in hard water, or lead ions in polluted water, or hexavalent chromium or something else, this chelating agent, this EDTA, will grab onto those metals and it will hold them tight using the lone pairs of all 6 of these atoms. Four oxygen atoms with their lone pairs and their negative charges, and two nitrogen atoms with their lone pairs each will hold that metal tight in its grip. It's like it's grabbing onto the metal, and because it's grabbing onto the metal ion, that metal ion is not allowed to do damage to your body when you ingest it, but not allowed to float around your body in your bloodstream either. So if this is in drinking water, it removes the metal, effectively removes the metal from the drinking water. If it's in your bloodstream, it'll effectively remove and detoxify your bloodstream from this particular metal ion. Chelating agents basically grab heavy metal ions and remove them from circulation. Literally in your body, physiologically, and from the water supply. So it's been used, it has been, and is still, don't let the 1950s fool you, it is still used today. And you can find this in soaps, laundry detergent, even shampoo. It's a water softening agent because it removes heavy metals like calcium and magnesium. I guess magnesium is not that heavy, but it can remove these kinds of metals from water. And the main thing that causes hard water are dissolved ions. So it's good for lead poisoning and other things like that, and for removing calcium. So chelation is basically the trapping of metal ions. And again, it can be used for lead. Okay, so that's a pretty interesting thing, but we're going to make use of this compound, hypothetically. I'll let you know of another thing. I mentioned that there were other kinds of indicators other than acid-base indicators. The indicator here, areochrome black T, or EBT for short, areochrome black T, it's an indicator that changes color not based on pH, although to use it, you actually do use this at a certain pH, and you actually have to put a buffer to make this yet work. Usually you apply a buffer between pH 9 and 10 and keep your solution between a pH of 9 and 10 for areochrome black to work. But its functioning as an indicator for the presence of metal ions actually has nothing to do with pH indicating. Okay, so it just works better at those pHs. So maybe I shouldn't even have mentioned it because that's just going to confuse the issue. Forget about what I just said. I mean, just put that aside now. Its main function in this context is to act as an indicator, not for pH, but instead for the presence or absence of these particular metal ions, like calcium or magnesium especially, but in this case, we'll use this for lead ion, because our example that we're going to look at very shortly is going to involve lead ions in a sample of drinking water. So areochrome black is an indicator. Its endpoint is the transition from red to blue or from blue to red. Okay, so it's an indicator that is red in the presence of metal ions. So if there are metal ions in the water, it's red. Once you have added enough of your EDTA to that water to remove all the metal ions, this areochrome black will turn blue in the absence of those metal ions. So if you once you've added just enough EDTA solution to your sample, all the metal ions just are gone, and areochrome black goes from red to blue. That's its endpoint. And that's also the equivalence point. But in this case, the equivalence point is not the equivalence between hydrogen and hydroxide ion, but it's the point at which your molarity or your moles of EDTA equal the moles of your metal ions. It's a 1-to-1 ratio. Every EDTA molecule traps exactly one metal. So it's a 1-to-1 ratio. So if you know how much EDTA you use, how many moles of EDTA you use, then at the point that this indicator, this EBT indicator turns blue, you will know that you have exactly how many moles of ion, in this case lead ion, you had in your sample of water. So we're going to use these facts together to actually do a titration that is not about acids and bases, but instead is to determine the concentration of lead in a sample of drinking water. And along the way, we're going to use some unusual adjustments to our molarities for the very small quantities we're dealing with. Okay, so here's the setup, and I'm going to repeat it on the next page as well. I'm going to repeat the question on the next page. A water sample, so this is some random drinking water sample, is titrated with a 1.6 micromolar solution of EDTA, micromolar. You can use metric system prefixes in front of anything you want. In this case, I'm using this prefix in front of the unit molarity, micromolar. What does that mean? That means I have 1/1,000,000th of a mole per liter. 1/1,000,000th of a mole per liter. Okay, so a water sample is titrated with 1.6 micromolar solution of EDTA. The EBT, that's the areochrome black, the indicator, turns from red to blue after dispensing 13.52 milliliters. So it turns to red to blue. In other words, at 13.52 milliliters of this very low concentration EDTA solution into 20 milliliters of the water sample is then devoid or has had all of its lead ions completely removed, just exactly completely removed at that point. In other words, at this point, the moles of EDTA equal the moles of lead. That's what I'm getting at. When we say EBT turns from red to blue, what we're saying is at exactly that point, moles of EDTA equal moles of lead 2 plus ion. So assume the mass of lead ions is insignificant. It's going to be insignificant because we're talking about parts per billion here, which means the mass of lead is really going to be virtually nothing in terms of the mass of the entire solution, because this is not even going to be per liter. This is going to be per kilogram of solution. So compared to a kilogram of solution, a few micrograms or nanograms or whatever of lead, whatever the answer is going to be, is not going to be significant. So your solution really isn't going to be changed by very much. So we're going to ignore the mass contribution of the lead ions to the mass of the entire solution. We're going to pretend that it's just the water that is the mass of our solution. So what is the lead ion concentration in parts per billion? The EPA sets the action limit on lead in drinking water at 15 micrograms per liter. Would you drink this water? You could probably tell by just me asking the question that the answer is probably no, right? If anyone hands you a glass of water and says, would you drink this? The answer is no. The answer is always going to be no. Doesn't matter what it is, just say no. The fact that they're asking already tells you should say no. Anyway, but let's compare the values. We're not just going to answer no. We're actually going to do the numerical calculations. We're going to see why we should say no. Okay, a water sample. Okay, this is the same exact setup. So just like before, now this all sounds very complicated, but my point in this is not to throw a bunch of complications at you. That's not the point of this problem. My point is that no matter how I dress it up, ultimately, we're just dealing with two of the same concepts we've been dealing with all along: unit conversions and concentrations. Molarity times volume equals moles. Everything we're doing comes down to unit conversions and molarity times volume equals moles, and maybe a little bit of parts per million. Okay, yeah, that too. But that's a conversion. That's a unit as well. That's a unit concentration unit conversion. So let's do this. Okay, first, we have 1.6 micromolar solution. So our molarity here turns out this time to be 1.6 micromolar solution of EDTA. So we multiply molarity times volume equals moles of lead ion. It equals molarity of EDTA, which will equal, equals moles of EDTA, which will equal moles of lead ion, right? In fact, here, just to make it absolutely clear, moles of EDTA, which will equal, by definition, moles of lead ion. So ultimately, we're just trying to figure out the moles of lead ion from multiplying the molarity of EDTA solution and the volume of that EDTA solution. So what's our volume of the EDTA solution? Well, that is in milliliters. Well, I can't just do this, right? 13.52 milliliters multiplied by micromolar. Well, those units aren't going to work out. Here's what I'm going to do. I have my choice. I can either convert the micromolar to a different unit, or I can convert the milliliters to a different unit. You know what I'm going to do? I am going to, let's see, I don't know. I'm actually not entirely sure what I'm going to do. I'm going to convert the milliliters to liters, because what does this mean? 1.6 micromoles of EDTA per every 1 liter. So if I multiply this by 0.01352 liters, the liters will cancel out and I'll have my moles of EDTA. Actually, no, I'll have micromoles of EDTA. That's okay, I can deal with just micromoles of EDTA. If I need to, I can always convert those to moles. So let's do it that way. So these two statements are exactly equivalent. All I did was transform the units to something a little bit more reasonable. So 1.6 multiplied by 0.01352 gets me to 2.163 times 10 to the negative 2 micromoles of EDTA, which equals exactly the same number, 2.163 times 10 to the minus 2 micromoles of lead ions. We know that because it's a 1-to-1 mole ratio of EDTA to lead. Every one EDTA molecule grabs up or snatches up one lead ion. So we know it's a 1-to-1 ratio. So once we figured out our EDTA moles, or micromoles in this case, we have our lead micromoles. Okay, so then the question is, what is the question? We're looking for, first question A, what is the lead ion concentration in parts per billion? Parts per billion. Well, what is the definition of parts per billion? ppb generally equals this. It equals, it equals micrograms of compound. In this case, our compound is lead 2, lead 2 plus, to kilograms of solution. That's one way to do it. Or you can just take grams over grams times 1 million. That's another way you can do it. Okay, well, so it looks like we have our work cut out for us because we don't have micrograms, do we? We don't have micrograms of our lead 2 plus, but we do have the number of micromoles. Okay, so let's see. If I take my micromoles, I don't think I really need scientific notation. I'm just going to write this as 0.02163 micromoles. I haven't changed anything, right? 10 to the minus 2 is 0.02. It's the same thing. 10 to the minus 2.2163 is the same thing as 0.02163. I haven't done any unit converting yet, so don't worry. It's still micromoles. Micromoles of lead, let's convert that to, we know that every 1 micromole of lead will equal 207.2 micrograms of lead. How do I know this? Well, if 1 mole equals 207 grams, then 1 micromole should equal 207 micrograms. All I'm doing really is on the bottom, I'm just dividing, or I should say, dividing by 1,000,000 on the bottom and dividing by 1,000,000 on the top. The dividing by 1,000,000 cancels out. And if you're not convinced, I can prove it to you. 0.02163 micromoles. We know that every 10 to the 6th micromoles equals 1 mole. And then we know that every 1 mole of lead, this is of lead, by the way, every 1 mole of lead gives us 207.2 grams of lead. This is from the periodic table, right? Look on the periodic table, you'll see the atomic mass of lead is 207.2. And then, since I want micrograms, I'm going to convert back again. I know that every 1 gram is 10 to the 6th micrograms of lead. So if I work all of this out, oh, what do you know? 10 to the 6 micrograms, 10 to the 6, 10 to the 6 and 10 to the 6 cancel each other out, not the grams, but the 10 to the 6 divides out the 10 to the 6, and I get 0.02163 multiplied by 207.2, which is exactly what I have here. They are exactly the same value. So whether I bother to convert or not, as long as I'm using the same metric prefix on the top and the bottom, it's actually the same ratio because the conversions would cancel each other out anyway. But again, if you're not comfortable with that, then just go through the step-by-step process, convert from micromoles to moles, from moles to grams, and grams back into micromoles. You'll get the same answer. It'll take you a little longer, but that's okay. It's better that you know what you're doing than you take shortcuts. Don't take shortcuts if you don't understand them. So I got 4.48 micrograms of lead. So that's 4.48 micrograms of lead. Now, what is the kilograms of solution? Well, where does it mention anything about the solution, or I should say about the water that this happened to be in? Oh, there it is. There's some piece of information, right? So my water that contained these 4.48 micrograms of lead, it was 20 milliliters of water. So I'm going to convert 20 milliliters of water into kilograms so I can make this parts per billion calculation work out. Well, I know that every 10 to the third milliliter, well, first of all, this is water, right? H2O. So let's first get this out of the way. We know that every 1 milliliter of water is 1 gram. That's the density of water. We've been talking about that since the beginning. Then we know that every 10 to the third grams is 1 kilogram. So what we end up with is 20. Yeah. 20 divided by 1,000. Sorry, that's I almost didn't see it again. It's right there. I almost missed it. 0.02. So that's 0.020000 whatever kilograms of H2O, which is kilograms of solution. Remember, we are going to assume the mass of the lead ions is insignificant. So I'm not going to bother adding the mass of these ions. Think about it. If I take 0.02 and add 0.000448 to 0.02, that's going to be beyond my significant figures anyway, right? I mean, just to prove, again, I will prove it. 0.02000 plus 4.48 micrograms, this is in kilograms. So 4.48 micrograms would be 0.00000000448 kilograms. When you add this up, you are essentially going to get 0.0222, and all that's going to disappear because it's not significant. So you're still going to get 0.02. It doesn't matter. The micrograms of lead are not going to significantly affect your kilograms of solution. So 0.020000 kilograms of solution. So micrograms divided by kilograms. In other words, 10 to the minus 6 divided by 10 to the third is 10 to the minus 9. That's by definition part per billion. So we end up with 4.48 divided by 0.02, 224 parts per billion. I don't know about you, but that sounds like a lot. In fact, that's 2.24 parts per million. It almost doesn't even make any sense to even bother reporting this in parts per billion. You might as well just say 2.24 parts per million, or sorry, 0.224 parts per million, because it's that close to part per million, which is a bigger value. Threefold or 3 magnitude difference in value almost. All right, so parts per billion. So that's our answer to part A, 224 parts per billion. So recap, all we did was take the molarity times the volume again. We just had to contend with some funny looking unit here, micromoles, but that didn't matter too much in the end because ultimately we wanted micromoles. So believe it or not, having that micromolar was actually a step of convenience for you because it meant one less unit conversion, because you ended up with getting micromoles, which you could easily convert to micrograms, which is what you needed to plug into your micrograms per kilogram of solution to get your parts per billion, because by definition, a part per billion is micrograms of compound of dissolved solute per kilogram of solution. So we got our micrograms divided by our kilogram solution. Where did we get our kilograms of solution? Our solution is the water itself. The water sample itself was 20 milliliters. 20 milliliters is 0.02 kilograms of water. Now, why were we able to get away with having a solution that is only made up of the solvent water and not the lead? Because the lead was too small to have a significant impact on the mass of the solution. Adding that tiny, tiny bit of lead, micrograms, compared to kilograms of solution, simply didn't do anything to the number. Once you add really tiny numbers to really large numbers, the tiny numbers kind of just get thrown out as being less than significant or insignificant. Okay, so even though I said that, you can prove it over here. It is indeed insignificant, meaning not significant. Our significant digits are not enough to cover that 4.48 micrograms of lead. So we end up with 224 parts per billion. Micrograms over kilograms. Okay. I was hoping I had some extra space for part B. Okay, I don't have any extra space for part B, so I'm going to have to do some erasing now. But I hope all of that made sense. MaVa equals moles. Take your moles, convert to grams or micrograms in this case. Once you have your grams, convert to whatever other unit you need that involves grams. Up until now, we've been doing molar mass, so grams per moles. This time we were doing parts per billion, so it was micrograms divided by kilograms of solution. Luckily, this time it wasn't an option. We really needed to know the volume and or mass of our solution in order to calculate part per billion, because that is a unit that depends on us knowing exactly how much solution we have. So it wasn't optional for me to give you that. Okay, let's do part B now. Part B actually depends again on exactly the same relationship. We're still going to need our micrograms. So I'm going to keep that 4.48. So everything we did up to calculating the 4.48 is still relevant to part B. The only thing we don't need, or not don't need, but the only thing we're going to do is we're not going to do the part per billion calculation, but instead we're going to take our micrograms and we're going to divide by what? Well, we're going to divide by liters. Well, that's not so bad. We've been doing that all along, moles per liter, and this time it's just going to take micrograms per liter. So we're just going to take our micrograms and divide by the number of liters of solution. What's our liters of solution? Well, it's 20 milliliters divided by 1,000 to give us 0.02 liters. In fact, this works out quite well for us. 20 milliliters, right? 20 milliliters of water. We don't even need to convert to grams, so let's get rid of that. All we really need to do is convert milliliters to liters. We know that every 1,000 milliliters is 1 liter. So that's going to be numerically, it's exactly the same thing. 0.02000 liters of water solution, or of water, either way. Again, it is solution, but technically the solute is so low in value that it almost doesn't even matter. And so what do we get? Not coincident. It's not a coincidence. We end up with the same exact value, 4.48 micrograms per 0.02 liters gives us exactly the same number, 224 micrograms per liter. Why do you suppose that is? But wait a minute, why did I do it that way? Because I wanted to compare to this number, 15 micrograms per liter. Would you drink this water? I don't know. I've got about 14 times the allowable amount of lead in my water at 224 micrograms per liter, right? 224 divided by 15. 224 divided by 15. Oh, no, sorry, almost 15, not even 14, 15 times. I've got 15 times the allowable amount of lead at 224, 15 times the amount of lead that's actionable, meaning at 15 micrograms, they come in, the guys in the hazmat suits come in and start making arrests. No, not really, not in these days. This is 224 micrograms. No, you should not be drinking this water. Definitely not. This is pure poison. But it's not a coincidence that our number ended up being exactly the same. Why do you suppose that is? Because a part per billion is exactly the same thing as a micro divided by a kilo, right? A micro is 10 to the minus 6. A kilo, well, I shouldn't say kilo, excuse me. Well, it is a kilo. A liter of water, remember, 1 liter of water is 1,000 milliliters, which is 1 kilogram of water. So this really is 10 to the minus 6 over 10 to the third. In terms of mass, this is 10 to the third, 10 to the minus 6 mass units divided by 10 to the positive 3 mass units. 10 to the minus 6 minus 3 equals 10 to the minus 9. That is, by definition, a 1 part per 1 billion. So it's not a coincidence that these two numbers numerically are exactly the same thing. They are expressing exactly the same kinds or the same relative orders of magnitude of units on the top and the bottom. By definition, a microgram per liter is a part per billion. So it's not a coincidence that the EPA expresses things this way. In fact, this is the SI unit. This is the SI, microgram per liter is an SI unit or makes use of SI units, whereas part per billion is a non-SI way unit of expressing concentration. Some departments will use parts per billion, and that they still do, but other departments will switch over to the International Scientific Standard units of the metric units, micrograms per liter or milligrams per liter for part per million or whatever, or nanograms per liter for part per trillion. So it's not a coincidence. Both answers are exactly the same thing because they are, by the way, when I say answer, we had to calculate in micrograms per liter simply to compare to the 15. 224 is much bigger than 15 micrograms per liter. We just needed to see that these things really are we are comparing apples to apples. So no, don't drink the water or whatever it is. Don't drink the lead juice. I prefer my water like I prefer my gasoline, unleaded. So these are the kinds of things you calculate. These are the kinds of real life calculations people do when they analyze water, for not just lead, but for other kinds of compounds. They do these sorts of things. Of course, that's probably done automated. It's probably automated with machinery that can do this quickly and easily, but not necessarily. Sometimes people will collect water samples and just analyze them through maybe partially automated processes, but somebody somewhere has to understand these concentrations and understand what they mean. And this is the kind of underlying math that allows for these sorts of analysis of unknown compounds or unknown quantities of compounds. So titration is actually a very useful chemical technique for analyzing substances. Not just for concentration, but also for figuring out what substance you actually have. And it's not limited to just acids and bases. Anytime you can figure out a situation where the moles of one thing equal the moles of the other, and you have some sort of visual indicator compound, like the acid-base indicators that we talked about, or the this chelating, this areochrome black tea indicator, anything that will give you a hint, well, not a hint, but will somehow tell you when the two moles are set equal to each other in real life, you can do a sort of titration. By the way, you're not limited to just visual indicators. There are other kinds of methods too. There are actually electrochemical methods that can tell you when you've reached a certain threshold of concentration of ions. As you know, electrolyte solutions conduct electrical current. So you know you have no more ions when the current stops, or when the current decreases below a certain threshold, you know you've reached a certain limit of reducing the amount of ions in your solution. So there are electrochemical ways of determining concentrations as well. You can relate the electrolyticity. You can relate the conductance of a solution to its concentration. And you can determine concentrations that way by building what's called a standardized curve. We're not going to go into that. Actually, that's not part of this class, but in future chemistry classes, you will do exactly that sort of thing. And you can also base it on absorptivity, molar absorption, meaning how much light passes through a solution. All of these are just different versions of this, measuring concentration of a solution and seeing how it affects other variables. This is probably the most obvious, most sort of concrete way to look at it, though. Okay, I hope that was very interesting. I hope that was interesting. I find this interesting. Gaining knowledge that you didn't have before about something by simply using what you already know to leverage more knowledge is the heart of science. I mean, that's one of the major things about science, is using what you know to find out what you don't know. That's how science builds upon itself. That's how you bootstrap a technologically advanced society, by using what you know to find new knowledge that you didn't have before. And this is just one small example of that. I hope you find this interesting, and I hope you work on this. I know this is complicated. I don't expect you to just take one look at this and go, aha, yeah, of course, that's exactly what I thought he would do. Don't worry, that's not the expectation here. Look over it. If you understand these concepts after looking over it 3, 4, 5 times, then that's great. I mean, that's my goal for you. If not, well, just know that these last 2 examples were a little bit more advanced. The more typical, introductory chemistry level is more like the first 2 examples. Those are more toward what I expect, what you should master these first 2 examples for sure. The other ones, well, hopefully by the next chemistry class, if you take one, it'll eventually, you'll get used to it. That's going to take some time though. All right, let me know how it's going. Let me know if you have any great ideas about what other things we can look at, what other applications we can apply, we can use titrations in. Let me know if you have any questions or comments, concerns, if you spotted any mistakes. If I made any mistakes, let me know. This is our last pre-recorded video. I don't think I have anything else. This is the last section, and this is the last topic of that last section. So I hope this was all of this was informative for you. Let me know how it's going. Contact me. I look forward to hearing from you. Take care, everyone. Bye-bye.